Hello and welcome to Like the Deep. A few days before, the PyTorch event happened on February 6th. Now, in that event, what do you think would have happened? What do you think got announced? Maybe a new PyTorch version, maybe a new way to run a big SOTA model on your local machine, or a completely new announcement of a SOTA model? No, none of those happened. Not even the open source big models that happened. It was all about optimization. Now, I think long gone are the era where dump more parameters and get more performance. Now, it's replaced by an era of system mastery. Today, it's not about who dumps the most number of parameters and the most number of MOE experts. It's about who has the best compilers and who has the most highly efficient mathematics around it. Today, we are going to decode all 11 conversations that happened on the PyTorch event, and let's jump in. To speak was Sriram Raghavan from IBM, who delivered a thesis that redefined the framework. He argued that PyTorch has evolved into a distributed operating system for AI. Just as Linux abstracted CPUs in the 90s, PyTorch's torch.compile, Dynamo, and the inductor now abstract the messy world of heterogeneous hardware. That is, whether you are using NVIDIA's H100, an AMD Instinct, or an IBM's own Sparse accelerator. The framework ensures that the unified execution graph is contained. You just write once and run anywhere, just like Java used to be before. That allows enterprise to scale without being held by a hostage of hardware availability. Now let's just think of this, what this really means. See, gone are the days where you need to go and tinker around CUDA code and convert it into HIP if you have to write to ROCm. You just need to write torch.compile for that CPU or for that specific hardware, and you're now done. So basically, it's abstracting to such a high level that you don't need to really worry about the hardware that you're working with, which means you can scale across cloud, across places, and maybe you can run the same code in your local and also run the same code in your development server or your production server. So it makes it all unified, like how Docker is. So it's a very new take on it. Next came Stephen Watt from Red Hat, and he reminded us that innovation is useless without reliability. Red Hat has become the third largest global contributor of PyTorch, focusing on hardening the code. They have streamed 60 stability fixes to the compiler stack, ensuring features like torch.compile work with mission-critical real environments. He specifically championed vLLM as the industrial standard for inference. By leveraging PagedAttention, vLLM solved a KV cache fragmentation problem that kills throughput in multi-tenant environments. In Stephen's words, in the enterprise, cool isn't enough, always on is the requirement. Now, really vLLM is something that simply changed the landscape for production inference, because it provided the concurrency and the throughput that we never got before. So with vLLM, things are just moving to the next level and people are really adopting AI into the production. Now came NVIDIA to flex its hardware muscles. Niket Agarwal from NVIDIA then showcased the raw math of the performance. He demonstrated a 16 times speedup with H200 architecture. That wasn't a single trick, it was a ladder of cumulative gains. He moved from FP32 to automated mixed precision AMP, then implemented scaled dot product SDPA to bypass memory efficiency bottlenecks. By fusing kernels by torch.compile and utilizing Transformers engine FP8 support, he showed that GPU is not a black box, it's a precision instrument. If you aren't optimizing every memory trip between HBM and SRAM, you are leaving 90% of your hardware's value on the floor. Exactly, last video we really saw what these are all about. We saw how flash attention really saves memory. We saw what SRAM is. We saw how that movement of data occurs between HBM and SRAM and how that is really slow. And hence, whenever you try to optimize your stuff around this SRAM and fit your data into SRAM and do all of your operations in it, you are absolutely fast and you make use of most of your hardware. And that was what NVIDIA speech was all about. And now, with the same NVIDIA came Megh Makwana. He addressed the distributed scaling of MOE architectures. MOE is basically a mixture of experts. We had seen this before. Basically, there are two different feed-forward networks that are jointed from the router, and based on what the token is, that is whatever the context around the token is, the router is routed to one of or few of those feed-forward networks, and those feed-forward networks only get activated. The rest remain deactivated. So only because some feed-forward networks are chosen, so these are called the active parameters, and these only decide the next word prediction logic. And this is how a model that can be good at code, math, everything that can live together. So whenever the token needs to really go to the math FFN activates. And the math FFN is basically trained only on math. That is, the expert is trained on whatever specialization that he or she is in. So like this, the MOE also achieves something in parallelism, and that's what he's talking about. DeepSeek or Grok offer massive capacity with a proportional compute cost, but they are a nightmare to parallelize. So Megh broke down expert parallelism, where individual experts are sharded across different devices. So basically, let's imagine there are multiple experts, one for coding, one for math. Now, instead of storing everything in a single machine, it is shared across GPUs. So it's tried to fit inside the SRAM, and the movement from HBM to SRAM is reduced. That is, the amount of loading operations are reduced, and therefore, because each expert is independent of each other, that is, whoever gets activated has to just pass through their FN, and they don't depend like vertically. So you can really have them on different machines, and whenever each one activates, they run super fast and you get the output. The technical challenge here is the token router logic that directs the token with specific experts. But there is something that NVIDIA came up with called Megatron core. That's to align the routing strategy with the underlying network topology, because you have different GPUs, distributed, the model weights are distributed. So you need to really route according to that, because you have the model reality has to be aware of the topology of the network, and that's what Megatron core is about. He showed how to maintain the scaling even as the cluster gets grown. And scaling is just about not more chips, but it's about the geometry of the data flow, and it's about more about networking. Now came Polymage Labs, a startup from IISc. Uday Bondhugula from Polymage Labs shifted the focus to compilers. He addresses that hardware programming wall, that manual CUDA tuning is no longer sustainable, because CUDA is a huge code. Like something that is 3 lines in Python takes literally 185 lines if you have to write it in CUDA. That is something that you just can't really maintain. Therefore, he came up something called polyblocks, which is using MLIR, that is multi-level intermediate representation. It is a compiler concept. That is basically, it is an intermediary between the actual source code and the byte code, and it sits to really transcribe itself to another form of code. So it is a part of LLVM project. If you have to know more about it, please check the description. I have provided the GitHub link for it. And it is about automating the loop tiling and operator fusion. By mathematically analyzing the computation blocks, Polyblock creates memory layout that fits perfectly into L1 L2 caches, that is the SRAM of the GPU. And because of this, there is a 3x speedup from Torch's own inductor on A10 GPUs where they tested. So we are moving from a world where kernels are dynamically generated to compilers that understand hardware better than humans do. So it's optimizing better than you do automatically, which is a boon for us. Now let's talk about one of the most significant shifts in Indic ecosystem. Abhigyan Raman from Sarvam AI led to the core thesis that the speech recognition is now an LLM problem. Historically, ASR followed an encoder-decoder paradigm. So think about Whisper, a speech-to-text model from OpenAI. These systems are text first, that is, they converted audio into text, and then this text was then fed to any model of your choice to really come up with the thinking and the reasoning and then come up with the answer. But this itself was a bottleneck, because when you convert audio into text, you lose a lot of detail. You lose your accent, you lose your temporal things, you lose a lot of tonal stuffs. So there are a lot of things that you lose now. So instead, Sarvam is saying, let's go into a decoder only LLM space, where audio is directly converted into discrete audio tokens, that is using a neural codec. These tokens are projected directly into the same latent vector space. And what he's exactly talking about is what we talked about as MEL spectrogram. You saw that, right? So in our previous video, we had discussed about audio tokens converted as an image of MEL spectrogram, and then this being fed as into VIT and then into the latent space to really read the audio. And with this, LLM really understands the tone, the nuance, this accent, and is really able to respond to you in the same way. And all these details which are lost when it was text has now been captured. So the speech as tokens approach collapses the boundary between hearing and understanding. And for a country like India, where 22 major languages are there and there are hundreds of different dialects, and it's visually impossible or it's unthinkable for us to even train with so many dialects around, it is very well possible that only when you feed direct audio with all the nuances to the LLM can really respond the same way that the user is speaking on. So the user really feels that the LLM has already been trained on whatever he or his language version is about. So now this is a multi-model frontier that Sarvam is leading, and let's talk about this more on later. Now back to NVIDIA, we move to the future of hardware with Prasad and Utkarsh. This was a deep dive into NVIDIA's Blackwell architecture and NVFP4. We are officially entering the 4-bit era, but how do you shrink a 32-bit float into 4 bits without losing the soul of the model? The answer was micro-block scaling. A traditional quantization, you have a single scale factor for the entire tensor. You have one outlier value, the entire tensor loses precision. But NVFP4 on Blackwell uses a much finer grain sharing, a scale factor across small group of weights. This allows the hardware to maintain high dynamic range while using only 4 bits per weight. So basically, they use statistical methods that are very fine-tuned in nature, very minuscule, and it captures even the slightest deviation, and then those are now compressed to 4 bits, which means the model doesn't lose even if there is some kinds of sparsity or some outliers in the weights. So this means that it a 2x throughput and a 50% reduction in memory bandwidth pressure. In the inference world, memory bandwidth is the ultimate bottleneck, because no matter if you have 5090 or 5060, your 8 GB or 12 GB VRAM is going to kill you, because you can't even run models beyond 4 billion parameters or maximum of 7 billion parameters. All the others, it's out of your reach. So now with NVFP4 quantization, models that are actually 30 billion parameter size are suddenly loadable inside your machine with 8 GB or 12 GB VRAM. Now this is where we are accelerating execution. This allows a trillion parameter MOE to run without the loud kind of low latency that makes autonomous agents possible. Combined with vLLM's PagedAttention and Kernel Fusion that we have already talked about, Blackwell is effectively removing the hardware ceiling that it has considered LLM deployment for the last 3 years. But wait a second, all this is only for NVIDIA's Blackwell version. The versions below it do not support the NVFP4, which means it takes some time till we really take the advantage of this. Next came Hugging Face, and they had 10 minutes and they stole the show. Aritra and Sayak Paul from Hugging Face delivered what I considered the Bhagavad Gita for kernel developers. Their session was a masterclass on arithmetic intensity. Most engineers think GPU is slow because of the compute, but in reality GPU is usually idle, as we talked before. It is waiting for the data to be traveled from HBM to SRAM where it can work. Now this is the communication tax. Now they explained that for the GPUs to go brrr, you need to increase your flops to performance per byte of data moved. And this is where optimized kernels, that is Kernel Fusion, comes in with Flash Attention 3, and Thunder Kittens came in. They used a tiled matrix multiplication to keep the resident SRAM so far and so long as possible, so that instead of doing one math operation and sending the result back to HBM, these kernels fuse multiple operations into single pieces. They also launched the kernels libraries, and Hugging Face is democratizing these high performance primitives so that developers in Bangalore and in India can write kernels that rival hand-tuned code from NVIDIA's core engineers. The goal is to maximize arithmetic intensity, squeezing every possible floating point operation out of the silicon before the next memory clock cycle. And if you want to build the fastest models, you stop thinking about layers and start thinking about memory access patterns. So you go deeper and deeper, but now Hugging Face says, bro, do not worry about the complexities of a kernel. You know what you have to do? Just say, use kernels equal to true, and then say kernels equal to some whatever kernel that you like to do. Thank you, Hugging Face, for making something that is as complex as GPU, kernel, and compilation of Vim, which is absolutely daunting if one mistake and then your entire process and progress has been shattered. And this kind of process, simplifying it to something like 2 parameters, is absolute beauty from Hugging Face, and I really wish them well for that. Now the final session was from IISc, where Dr. Sen came up with approximating computing. She told that for small models and models where you can easily train them and you have a large amount of data, you can really come up with approximation instead of really doing accurate computing. And these approximations turn out to be very well with the accuracy metrics that you don't need to really spend your real compute and money on something as costly as GPUs. So this is a very interesting find, and if this is very successful, it might be proving very well for us, because all we have is like CPUs that are being commoditized all over the market. Now next came KLA on Qtile, and that reminded us how far AI has gone to be the backbone of everything from semiconductor manufacturing to sustainable computing. It has been revolutionizing every single part of the industry or the field that it has reached for. Now, but my personal highlight was meeting Abhigyan Raman from Sarvam AI outside the show. Now, I walked him through my project, that is the Sarvam 1 VL that I launched few days back before the conference. A fine-tuned version of 23 VL optimized specifically for Indic multimodal datasets, and discussing the future of Indic AI with somewhere as the forefront of the audio LLM and the Indic AI was the surreal moment. And next came discussing the video ideas and lot of things front and back, and I learnt a lot from Aritra and Sayak Paul. They had taught a lot of stuff about diffusers. They have discussions. I think his mouth kept on and on and on like a marathon, and discussing about what they do and commenting on the contributors and encouraging us to be a part of the community by also giving us goodies and giving us a free pro subscription for I think 1 month is a great thing that they did, and I really hope that we have more conferences like this. But the message from Bangalore is very clear. The stack is stabilizing. We have hardware from Blackwell and frameworks like PyTorch. And with kernels from Hugging Face, the only thing that is missing is what you build next. We have moved from training models to building systems. The latent space is open, and let's get the work started.